So if you have two sources of light, the sources will create an interference pattern. And this is like a screen over here, right? This middle part right here, this thing right here is exactly the same distance from this source to this source. So it's 0 wavelengths difference. This dark spot is actually a half a wavelength closer to this one than this one, so we get destructive interference. And then this one is 1 wavelength closer to this one than we are to this one, right? Now that's with two sources. You can do the same thing though if you use diffraction slits like this. So what's going to happen here? Let's just look at one slit. Okay, with one slit, you can see the light comes across, and when it hits that slit, it diffracts. It spreads out. Now it's more intense in the middle and much less intense on the edge, and you can see sort of that pattern like that. Okay. Now if I use two slits, then I have two diffraction patterns, and where they overlap, we get the same thing. We get an interference pattern on the screen, right? And again, this spot right here is exactly the same distance from this slit as it is to this slit, and the slits in this case are just acting like sources. Okay. This is a half a wavelength closer to this slit than this slit. And this is 1 wavelength closer to this one than it is to this one. Okay, so that's what's going on. That's physically what's going on when we look at interference patterns with slits like that. Okay, let's do a little mathematics here. Okay, so again, what's happening here is if we are right in the center here, we are exactly the same distance from this slit as we are from this one, right? At some distance to the side, if you can imagine this, and we call this distance to the screen, we'll call that big D, right? At some distance to the side, we might get another constructive interference, right? But we're two different distances, right? So we're this distance from that slit, sorry, it's hard to do that, right? And this distance from that one, right? So what we have to do is we have to come up with a way to figure out how much farther we are, so we can make these guys the same length, right? How much farther are we from slit 2 than we are from slit 1? Well, that's what's going on here, right? You can look at this diagram, okay? If you imagine some spot that's, in this direction, right? There's distance 1 and distance 2. Well, the difference is this little bit right there, okay? So if little d is the slit separation, then that difference in distance is just d sine theta, and that's what's going on in this formula. Okay, so the difference in distance is d sine theta, right? Which is theta is also, by the way, the distance that we are from the center, right? It's also here. I'll erase. It's also theta is also this angle here. Okay, they're the same angle. Okay, so it's d sine theta is the difference in distance, and when that's equal to an even number of wavelengths, you get constructive interference. Okay, and if it's, by the way, if it's n plus 1/2, and n is of course 0, 1, 2, 3, right? If it's n plus 1/2, and this is not in the data packet, is equal to d sine theta, then we will get destructive interference. Okay, so constructive interference is what the formula in the data packet is for, and then if you just sort of think about it, right, we can come up with one for destructive interference. Okay, now n is the order, they call it the order, right? So this is n is 1, this is n is 2, there's 1 on each side, right? 1 wavelength closer to the top slit, 1 wavelength closer to the bottom slit. This is 2 wavelengths, 3 wavelengths, right? The farther out you get, the fainter it gets, and that's because the light doesn't diffract all that far, it doesn't spread out. Diffraction is just spreading out like that, okay? And then this would be 1/2 wavelength closer to the top slit, 1.5 wavelengths, 2.5, 3.5. Okay, that's what's going on there. Now, there's another cool formula, and that's this guy right here. Okay, and this is the small angle. So if the angle is really small, that's like 1 or 2 degrees, right? Then we can use this one, right? And let me just explain what this is. So the big D is our distance to the screen. S is going to be this distance here. Right? And if you think about that, there's a little triangle there. Whoops, I meant that to go like this. There we go. Okay, there's a triangle there. And what we can say is small is to big, right? And then if we look at this guy, the small is to big, right? So we can go wavelength is to D, right? These guys are similar triangle. This triangle is similar to this triangle, okay? if the angle's small, if the angle's really, really small. And so then we end up with this, right? So S is the distance on the screen. D is how far away the screen is. And then little d is the separation. So in this diagram here, it's this distance here. Actually, it's to the center of the slit is what it is, right? That's the little d. Okay, little d is this. Okay. So again, this is our order. This is our wavelength of light. That's the slit separation. And then that's the angle off of straight ahead. If you picture this, right? These guys are going there. That's that angle right there. Okay. So write those down. Make sure you got those in your notes. In the next video, we'll use this to solve some problems.